and welcome to Cooking with Dr. T. Today, we're going to make salt water and really talk about the solubility limits and how materials become soluble and at what temperatures. So salt water is an easy example of something that's made of at least two different objects, in this case, salt and water. So let's go ahead and make some salt water by mixing together our two objects. So I have some coarse table salt, and I'm just going to take a spoonful of my salt. I'm going to dump it in with water. What do you think? Do we expect those to mix together? What we might expect is that the salt is staying in the glass, but as a solid. And if I were to actually dump my ice out, I can actually see that the bottom of my glass is filled in the sides with small particles of salt. Well, it looks like our experiment with mixing solid water and salt was kind of a bust. And you might not think that's surprising, but it turns out there are a few elements that are soluble as liquids or solids, completely soluble, but it has to do with the atomic radius, it has to do with the atomic structure, the lattice structure of the cell, and we'll get to that a little bit later in the class. But what we might be able to do is actually mix our salt with liquid water. So I actually have 2 glasses of liquid water here that are both different temperatures. So I have the thermometer, and we're going to go ahead and place the thermometer in each glass. So we have room temperature water sitting at about 73 degrees and our hot water at 174 degrees. So here's what we're going to do. We're going to take a little bit of this salt and try to put the same amount in each glass. So we've got the same amount of salt. We have our hot water and our room temperature, slightly cold water. And let's see what happens. I could stop right away, and you should be able to see one is clearer than the other. If we look from above, we can see that in the warm water, the salt has completely dissolved, but in the cold water, we still have salt crystals on the bottom of the glass. So apparently, temperature plays a part in how soluble a material is in another material. And it actually turns out that by combining 2 elements together, you can actually change the melting point and the boiling point. And we're going to see that using phase diagrams. Of course, there's always a point where we can't get any more soluble, known as the solubility limit. And over here, I have a glass that I've just been adding salt to and adding salt to and stirring it and stirring it. And you can see it's very cloudy. And we can see when we look from above, there's still a lot of salt solids in the bottom of the glass because we've reached the solubility limit of salt in water. Well, that's it for this episode of Cooking with Dr. T. I hope you learned something about solubility, because solubility is key when we want to alloy metals so that we can change their behavior, so that we can get stronger steels or more ductile steels or more weather-resistant metals. In fact, stay tuned for just a few more minutes and we'll talk about that idea just a little bit. So just looking at salt and water and talking about solubility, you might ask, why does solubility matter? Well, solubility, first off, let's just make sure we understand the limit, right? Whether you're liquid, solid, or vapor, it's that maximum amount of one component that can be dissolved in another. So alcohol has unlimited solubility in water, where sugar has limited, you can reach a limit like we did with the salt, and oil is insoluble. Now, why does this matter? Well, steel is actually iron with a small amount of carbon mixed in. But carbon is only fully soluble in iron if you add no more than 0.022%. And what happens is that carbon is held interstitially between the iron atoms because carbon's radius is less than half of the radius of an iron atom. And so it can hold 0.022% by weight and have no change to the lattice of the iron structure, and it basically still behaves like pure iron. Now on the opposite spectrum, if you add more than 6.7% by weight, you don't have any behavior even close to iron, and you end up with iron carbide, which is pure cast iron. It's very strong, but it's hard and brittle. You might be familiar with a cast iron, and that's probably not even pure cast iron, so less than 6.7% by weight. Now, if you get somewhere in between, then you can get some of the hardness and strength, but still some of the ductility and malleability of pure iron. And so common steels have carbon content somewhere between 0.12% and 0.3% to get that ideal combination for whatever the purpose that steel is for, but you can still get that nice hardness and strength of your cast iron. So an idea of what that might look like. So this is cast iron, it's not pure cast iron. This is 4% carbon inside of the iron. And what we're actually going to see here is because there's 4%, this idea of it being held interstitially no longer applies. And instead we see a number of different phase structures. So the first, those long gray ribbons, that's pure graphite. That's pure carbon in its graphite structure. Carbon's cool. It can be a solid in different forms. Graphite, diamond, it has these options. It's called an allotrope. Now, we also see within here grains that are literally the same that what steel is made of. We zoom in a little bit. Here's one grain, here's another grain, and another grain. And because we can't hold the carbon interstitially, instead, those layers, those black and white lines, are made up of either pure iron with a body-centered cubic structure, BCCFe, or iron carbide, that Fe3 carbon. Now, it's really a challenge and a task for a materials engineer to say, all right, well, what if I had 2% or 3% carbon and I'm at a certain temperature? Will it bond? Will it be soluble? Because we saw temperature mattered. And we use something called phase diagrams to be able to visualize based on the percent of carbon by weight, which we can see on the bottom axis, and the temperature on the vertical axes, what behavior will we have? And the red line tells us when we transition from liquid to solid, and you can see that changes based on the percent of carbon. Now, this is super tricky, but we will get to where you basically understand this chart. But the way to do that is to start with the binary phase diagram for two soluble elements. These are elements that are not only soluble as liquids, but as they solidify, the atoms are interchangeable in the lattice structure, and so they can then interchange as solids. So that's going to be our next video, so join me in understanding how to read a binary phase diagram.